nuclear fission, fusion, and nuclear binding energy. So one thing that you might have heard very commonly, or common use of nuclear these radioactive isotopes, is its use in radioisotopic dating, which means we can tell how old the sample is, or how old a fossil is, how many years old the fossil is, whenever it's found, right? And how can we do that? That is usually done by radioisotope dating. So we just saw the use of this formula, which is the integrated rate law for radioactive decay. So if I know how much of a radioactive sample is present now, I can measure it, how much of the sample was present initially, and I know T half of my sample, I can calculate how much time has passed since that sample was first created. And that's exactly is radio isotopic dating. So for this, what we need is, in the sample that is found, in any sample that we want to know the life of, the age of, we just need to find a radio active substance that can be used. So there's one very common approach which is used, which is radiocarbon dating. In this case, we measure the relative amount of carbon 14 and carbon 12 present in the sample. Every biological sample, every living organism basically has a mix of carbon 14 and carbon 12, and this ratio of 14 to 12 is same for all living organisms as long as they are alive. But once the organism dies, the amount of carbon 14 starts to decrease as it decays to form nitrogen 14. So since carbon 14 decays at a predictable rate, we know what is the half-life of carbon 14. We have measured it, so it's in our records. We know that, and based on that, if I can measure how much carbon 14 ratio is present now, what should have been the ratio when it was living, that ratio we can plug in here. Initial ratio, final ratio. Initial ratio is same for every living organism. Divide by the final ratio that we found in that dead fossil, and T half, from there we can measure what is the T, or time, that has passed since the organism has died, and that is how we can figure out how old that fossil is. Another ratios that can be used to determine is K40 to argon 40, which is used usually to find the age of certain rocks. Similarly, there are other isotopes that are specifically found in different types of samples, and we can use that to measure the life of any fossil. Now, regarding nuclear reactions, we all have heard at some point that the nuclear reactions are really high in energy, and they can help solve all the energy problems for us, right? So let's look into what exactly are these nuclear reactions that we are talking about. There are two major kinds. First is called the nuclear fission, and the second one is nuclear fusion. We will not talk about these in too much details, okay? So we'll just briefly, superficially learn what these are. Nuclear fission basically means breakdown, okay? So nuclear fission involves splitting of large nuclei into smaller nuclei, and to do this we usually use neutron bombardment. So for example, we'll take a very large unstable sample. So this is unstable, okay, this is uranium, unstable uranium, and we bombard this with neutron. If you bombard, it reacts with one of the neutrons in a very explosive manner, okay? It breaks apart and it releases a lot of energy, okay? Along with releasing energy, the products you can see here, when this reaction occurs, it produces krypton, barium, and 3 neutrons are produced, and more energy, very high amount of energy is produced. This energy that is produced is basically the nuclear energy, and all these nuclear reactions usually are accompanied by very high, large amount of nuclear energy. But that's not the only interesting part here. The interesting part is there's 3 neutrons that are produced. We, as a reactant, only used 1 neutron, and now from this one atom, it disintegrated, but along with disintegration, it also produced 3 more neutrons. And these 3 neutrons can now go and separately, they can disintegrate 3 more of the uranium atoms. and each of these uranium atoms will further produce 3 more neutrons, right? And each of these 3 more neutrons can go and further affect 3 more uranium atoms each. So because of this process, sometimes the process becomes, well, not sometimes, most of the times this leads into a chain reaction when you only have to give power to one reaction to occur, and then this chain of reactions continuously keeps on occurring. There's a sequence of these reactions, and a lot of times these reactions are uncontrollable. Okay, so if these are not controlled, these nuclear reactions will never stop. Once you begin it, it will keep on continue to happen unless all of this uranium atoms that are present, they are disintegrated. Okay, so each of these neutrons may react with another nucleus, causing more reactions and increasing the number of neutrons being ejected, resulting in a sequence of reactions called a chain reaction. But now scientists have figured out a way to control these reactions. We usually perform such reactions in a reactor with very controlled environment. There's very cold bars or regions that are used to perform these reactions in a controllable manner. Okay, but it's very easy for these to, again, if you lose control, these can go completely out of hand. But there are reactors that are used to perform these reactions in a controlled manner. Then there's nuclear fusion, which is another type of reaction, nuclear reaction. Here, smaller, lighter nuclei usually combine to form a heavier nucleus in the process called fusion. So fusion just means things are fusing together, they are joining. For example, this hydrogen 2 and hydrogen 3, they combine together and they produce helium 4, and along with this they are releasing very high amount of energy. This is the type of reaction that is found in sun. Okay, that keeps happening in sun. So nuclear fusion can also be a source of very high amount of energy. Okay, now the question is, where is all this extra energy coming from? Why are these reactions so high in energy? Okay, so if you remember previously, we saw that there's a very strong force that is present inside the nucleus, protons and neutrons, and there's a very strong force that's keeping it together. There's a very strong force that's repelling it as well. There's a balance between the two, right? But whenever this nuclear reaction occurs, there's always a mass, a very small amount of mass that is lost. Okay, and that mass that is lost, that is equivalent to a certain amount of energy, and that is called as nuclear binding energy. This is the energy that binds the nucleus together, and this is the energy that is needed if you want to break the nucleus apart, right? So if this is the amount of energy that is holding the nucleus, you apply that much energy on the nucleus and nucleus will break apart. So that is called the nuclear binding energy. It basically is given by this formula, E is mc square. This is not actually nuclear binding energy formula. This is the formula which relates the mass and energy. So mass is always related to energy. How? By this. E is equal to mc square. Delta E is delta mc square. Delta here stands for change. So what is the change in energy that occurs in a nuclear reaction? It is equivalent to the change in the mass that occurs in the reaction times c square. So what is this? This is delta E is the change in energy, delta M is the change in mass, and delta C is the speed of light. 2.99 times 10 raised to power 8 meter second square. Actually, this should be meter per second square. This mass here is usually measured in kgs. Not usually, it should always be measured in kgs, and I'll show you that right here. Okay, so the nuclear binding energy is the energy produced when the atom's nucleons are bound together. This is also the energy needed to break a nucleus into its constituent nucleons, meaning protons and neutrons. Okay, how do we find it? You find what is the mass difference between the formation of an atom or a nucleus. What is that? That would be mass of all the nucleons combined minus mass of nucleus. What are nucleus? Remember, nucleus means nucleons. Nucleons means neutrons and protons. So you will take mass of all the protons plus mass of all the neutrons, that's your mass of nucleons, minus the mass of your atom, which is the mass of the nucleus, right? So this is mass of nucleons minus mass of your atom. The difference is called as delta M, and you find that delta M, you plug it into this formula, where E is energy, M is mass, C is speed of light, M should be in kilograms, and unit of E will be kilograms times meter squares per second square. Okay, and when you get this, know that 1 kg meter square second square is equal to 1 joule. So basically whatever you calculate is equal in joules. Okay, let's try questions on this. For example, calculate the binding energy per nucleon of carbon 12. Per nucleon means I need to it's not asking what is the binding energy of this atom, it's asking what is the binding energy of this atom per nucleon, meaning I have to divide it by each nucleon, total number of nucleons. Okay, so first let's find what is the carbon 12 means. 6 carbon 12 means how many protons? Number of protons is 6. Why? Because this number right here, Z, is 6. Then number of neutrons will be 12 minus 6 from here, because this is 12, so 12 minus 6, which is also 6. So it's 6 protons, 6 neutrons. So mass delta M will be mass of protons plus mass of neutrons minus mass of atom. Mass of atom is given to you. Please ignore this. Mass of atom is given to you, which will go right here. Mass of proton, this is mass of 1 proton. How many do we have? We have 6. So this would be times 6 right here. Mass of neutrons, also this is mass of 1 neutron. We have 6 of these, so times 6, that would go here. From here we'll find mass of change in mass, but this unit will be AMU. You can see right here, this is the unit U for the mass. Okay, then the next step is we have to convert this U into kg, because remember, in case of E, delta E is delta mc square. This delta M needs to be in kg. How would we convert this to kg? This is a very simple formula. Okay, so first you find this, what we just saw. Okay, once you have this, we find delta M in kg, which is you take this number delta M, you divide it by the number of units that you have, which is Avogadro number, and then convert it into kg. So 1 kg is 1000 grams, and 1 gram is 6.022 times 10 raised to power 23 AMU, if you guys remember. Okay, so we use this formula to convert U into grams, and then we convert grams into kgs using 1 kg is 1000 grams. So from here we'll find kg, then you multiply it with C squared, which will give you your energy in joules. Don't worry about these units. As long as this is kg and this is meter per second squared, your final answer you can assume is joules, because one of these is same as joules. Now this is how much nuclear binding energy is in carbon 12, if the question asks. But the question is asking per nucleon. So we divide this by number of nucleons. And how many number of nucleons do we have in total? 6 protons and 6 neutrons. So total is 12. So you take it and you divide by 12. So that's the process to find your nuclear binding energy for any atom. There's one more example here. I would briefly explain it. You guys can try this on your own. Iron 56 is an extremely stable nuclide. Compute the binding energy per nucleon again for Fe56. Mass of the atom is given. Mass of 1 proton. Remember, H1 is proton and neutron is also given. Again, we look at iron 56, Fe56, which means it has 56 protons plus neutrons. But how many protons? Where do you find this number? From periodic table. And periodic table will tell you this is 26. So it has 26 protons, which means neutrons will be 56 minus 26, that is 30. So my delta M will be mass of 26 protons plus mass of 30 neutrons added together minus mass of atom. So you take 26 times this, 30 times this, and then minus this right there. This will give you your answer in U. Now you take the U, you multiply it with 1 gram is 6.022 times 10 raised to power 23 U and U gone, your answer is in grams. Now we convert this to kilograms. 1 kg, 1000 grams. Grams gone, and your delta M is now in kg. Once you have this in kg, multiply this by delta M times C square, and that is your answer for number of nuclear binding energy. But the question is asking again per nucleon, so you take this number which is your E, delta E, and then you take your delta E divided by total nucleon which is 56, and that is your final answer. It's all written right here.